In a previous video, I took apart a Droid personality chip, analyzed the circuit, and created this schematic. The goal is to eventually use this schematic to create a new personality chip PCB. The next step towards that goal is to create the schematic in a utility called an Electronic Design Automation Tool, or EDA for short. There are a lot of different EDAs out there. I'm not going to talk about any of them except for two. The first one that I want to quickly cover or mention is KiCad. KiCad is free. You can download it. It is supported across multiple platforms. It has everything you need to design your own PCB, and then it will generate the appropriate files that you would then upload to a company that will then manufacture the PCB for you, such as OSH Park. KiCad is not what I used for the personality chip. What I used for the personality chip is another EDA that's free called Easy EDA. This is web-based. They do have a version that you can download on your desktop, but I like that it's web-based in that I can switch from computer to computer to use this and not have to worry about installing new software. The other thing that I like about this is I plan to share the files when I'm done. I can share a link directly to Easy EDA of the project that will have the schematic and the PCB designs on it that you could then open up in your browser and play around with just to get a feel for things. If you create an Easy EDA account, which is free, you can then save that project to your own account, and you can modify it however you want, and have Easy EDA generate the PCB design files for you that you can then go ahead and upload yourself to OSH Park or some other company that will manufacture PCBs. So that's why I'm going to go with Easy EDA. KiCad is probably more sophisticated, it's probably better, and it's free. There is every reason to use this and not Easy EDA, but I'm going to stick with Easy EDA. Again, because it's what I'm familiar with and it's convenient. Okay, let's begin. So here is the user interface. I'm going to start a new project. Now, I'm not going to cover every mouse click here. I'm not going to go over every feature of this of Easy EDA, mainly because I'd like this video to be fairly brief, and by fairly I mean under an hour. There are tons of other YouTube videos out there that will cover all aspects of how to use Easy EDA or KiCad or any other EDA that's out there. So this is more just to give you a taste of what it's like. If you are interested in doing stuff like this, there are more resources out there that are easy to find, again, through YouTube or search online for other places. There's tons of information out there about this stuff. Okay, the project is going to be called Droid Personality Chip. I would call it a custom Droid Personality Chip. Okay, and the first thing it does is it creates this empty sheet here. This is where I'm going to create the schematic. And to begin, I'll go back and look at the schematic, and at the core here I see there is that memory chip. If I come over here to the component library, I can just type in this case, the product number of that memory chip that's used in the personality chips, the stock ones. That's the Puya P25Q80H, and it's going to come up with several different variations of that chip. The different variations are different packages that the chip can come in. Which one should you select? And does it have to be a Puya? Could it be a wind bond chip? Maybe you've got a bunch that you want to use already, or that's the one that you saw in my link to Mouser from one of the old OSH Park personality chip links that I've shared in the past. Yeah, you can go ahead and do that. Ultimately, though, it doesn't matter because the pinout, whether it's a Puya or a WinBond or anything else, anything in this 8-pin 25 series flash memory chip, it's going to have the same pinout. So you can get away with using any one that you want. But since this is the chip that personality chips use, the stock ones, I figured I'd start out with this. So which one do you pick? Well, you can look at the datasheet and look at the different packages that are identified in the datasheet. I can tell you that the one that we want to use is this that's marked an SOIC 8 version of this chip. There is also an SOP 8 version. What's the difference between the two? If you look on the right here, you'll see a footprint and you'll even see a picture of the actual chip. The difference between the SOP 8 and the SOIC 8 is this. If you look in the Puya datasheet, it talks about two different versions of an SOP 8 package. One is 150 mils and the other is 200 mils, I believe it was. And that's just that's referring to the width of the package itself, this black piece of plastic here. The one that is used in stock personality chips is the smaller package, the 150 mils package. So which one of these two is the 150 mil version? Well, if you look at the footprint name here that has like L 4.9, W 3.9, that's referring to the length and the width. And in this case, it's using millimeters instead of mils. And the smaller one, which has a length of 4.9 and a width of 3.9 versus the SOP 8 one here. That's the one that's in the personality chip. That's the one I'm going to use. So I'm going to select that. I'm going to click place, and it's now in the schematic. And I can put multiples of them here if I want, or I can hit the escape key or the right click with my mouse, and it goes away. So I only have the one on the schematic. So now the next thing to do is to start placing components from the schematic, and luckily there aren't that many to do. For example, we can start with the power here. We see on the schematic it's referred to as VDD or VCC, and it connects to pins 7 and 8, the hold pin and the VCC pin. Well, if we look over here in our schematic, we can see pin 8 is VCC, pin 7 is hold. Let's wire those up to VCC. So in the top right here, there's a little box called wiring tools, and there's a VCC symbol right there. So I'm just going to click on that, and I brought it to the schematic here. And now I need to connect it to the pins. The first item in this wiring tools section, it looks like a line with a couple right angles in it with circles on either end of it. That is the equivalent of a wire for the schematic. And now I'm just clicking the pin, and then I'm bringing it out and connecting it to VCC. The red dot means that the two wires coming in, or all the wires coming into that section there, are connected together. So what I've done is I've connected pins 7 and 8 to VCC. Now if we go back, I have a ground connected to pin 4. Come back to the schematic here. Get rid of this menu. There. And again, under wiring tools, I have some symbols here, including this sort of arrow looking thing pointing down. That is ground. I can click on that, bring that over here, and connect that to pin 4. Now you might notice there's another symbol for ground here, and in fact there are, I believe, up to 4 different symbols for ground. They all mean the same thing for our purposes anyways. You can use any one that you want. It doesn't matter. You can use different ones in the same schematic if you want. It doesn't matter for this circuit, which is small and simple. But I'm going to choose to stick with my arrow pointing down symbol that I've used in the original schematic that I drew. So the next thing now to look at is, well, let's look at pin 3 here, the write protect pin. We can see that there's a R33 here. That's a resistor, and it's got a value of 10 kiloohms, and I need to put that into my schematic. And now Where is the resistor value or the resistor symbol? There's nothing like that up here in wiring tools. Instead, I have to come over here to the left where it says EELib. And if I click on that, I get a bunch of common objects that are found in circuits, such as resistors, capacitors, inductors, and connectors or headers. So up here are the resistors. There are two different versions. They're the same thing, they mean the same thing, it's just which symbol do you prefer to have in your schematic. You can use this little squiggly line here or this little box symbol here. They both mean resistors, or they both represent resistors. Since I used the box version in the schematic that I drew, I'll stick with the box version here. But the other thing worth noting is underneath all of these symbols here is a bunch of text, and that's referring to, in the case of the resistors and the capacitors anyways, the footprint for that component. The footprint is how that component is going to be represented on the PCB. For example, if it's a through-hole component, the footprint will have, in the case of a resistor, which would have two ends to it, it would have two holes. The leads for the resistor then would go through those holes. For surface mount components, there would be two exposed copper pads on the PCB for a resistor. How big those pads are and how far apart they are will depend on the size of the resistor that you decide to use in your PCB design. There are several different versions here. The ones that begin with R underscore and then a big number, those are referring to different surface mount, standard surface mount component footprints. I am going to go with 0805. There are many different sizes. In this case, it's going from smaller ones at the top. 0201 is very, very tiny, all the way down to this 2512 package, which is pretty big, and then into the through-hole versions, which are all marked as axials here. I'm going to use 0805. Why am I using 0805? It's a good balance between being a small component but still being large enough that you can solder it with your hands. When you get to really tiny components, soldering by hand is possible but not practical. So 0805 is what I'm going to go with here. If you want smaller resistors or smaller capacitors or bigger ones, or say you want to do an all through-hole version of a personality chip, which would be kind of interesting, you could pick one of those. It is entirely up to you. There is no right or wrong here. It is just what you prefer. In all of my personality chips, I'm using 0805 components. I'm not going to change that now. So there is my resistor, and I'll wire it up here to the right protect pin. Where I place it on the schematic doesn't matter. Again, it's about how these things are connected, not where they're placed, not how pretty the schematic is. Put it wherever you want to put it. Just make sure that it's connected up to the correct pin. I'm going to leave it about there, and I need to add that or connect that to ground, so I'll go grab another ground symbol and connect it like that. There is a value here for its to represent its resistance, or it's the resistor's value. This is not something that you need to specify here. You could leave it at its default value, because when you build the PCB manufacturer doesn't know or doesn't care what value resistor you're going to be putting there. It just cares about the footprint that it should be using. But it's good to put the value in here as a note to yourself so that you can refer back to it later. So that is what I'm doing here. I'm putting this in as 10K. It's a 10 kilo ohm resistor. The R1 above that is a reference designator. Every component on the board is going to have a reference designator. It's usually a single letter followed by a number. So for example, the memory chip that I put down earlier has a reference designator of U1. And this has R1. And Easy EDA will then increment the number automatically for you. You don't have to keep changing it. But I am going to change it. I want it to match the reference designator that is on the stock personality chip. In this case, it's R33. So I rename this R33. The next thing I need to add is this capacitor here, C42, which is connected between power and ground. So I'll just create a little power symbol here. I'll grab a capacitor. I'm going to make sure that I set this to 0805. I'm going to hit the R key on my keyboard to rotate it so it's vertical instead of horizontal. And then I'll attach it to ground. Now I could take this and stick it over here. And I could even run a big long wire all the way over here to ground if I wanted. Again, perfectly valid. The capacitor is still connected between VCC and ground. So from a schematic standpoint, it's wired up correctly, but it's not as readable to me. So I prefer to keep this off to the side like that. Again, there's no right or wrong here. It is up to you. You can place the components on the schematic however you want, whatever makes sense to you, whatever looks readable to you or good to you. It is your choice. That capacitor has a reference designator of C42 and a value of 100 nanofarads. Now this says 0.1 microfarads, which is 100 nanofarads. So I could leave it like this. I could type it in as 100 NF if I wanted. It is entirely up to you on what you prefer it to say. And I'm going to go with 100 NF because that is what I wrote in my schematic. And what else do we have? We have a capacitor over here, C44, that's connected to the clock pin, pin 6. So again, I'll grab a capacitor, bring it over here like so. I'm going to connect that to ground. And also connect it to the clock pin. And that has a value of, my schematic here says 5 picofarad. We saw in the previous video when I measured it, it's actually 10 picofarad. So I will correctly identify it as such with a reference designator of C44. And that is pretty much the schematic. That is what I wrote down or drew here. It is now formalized in the schematic here. I'm going to save this while I'm here. And at this point, we could try to go and create the PCB itself. But before I go and create the PCB, I need to know the dimensions of the PCB. So I am going to use the stock personality chip as reference, and I'm going to measure it. And I'm going to measure it using these cheap electronic calipers that I bought off of eBay, which are surprisingly accurate here. So I want to make a quick record here of the chip. Basic diagram. I'm looking for the height. I'm looking for the width. And they're going to be those gold fingers here. Good enough. And I want to know those as what the height of those or the length of those. And I'm also going to want to know, I should call that H1 or HF. I suppose I should call the width WF. And I need to document those. So the height of the fingers, the width of the fingers. And I should probably also document the pitch, although I don't have to because I already know what it is. So let's get to this. Should be very simple. Now I can measure, I have the option to measure in inches or in millimeters. I am going to make the choice here to measure in inches because I believe the original designers of this PCB designed in inches, or more accurately, they designed using mils or thousandths of an inch. So in this case, this is currently reading, well, it was reading, well, now it's reading 1 mil, or we go a little bit wider here, 25 mils. So I'm going to do my measurements in mils here. The reason I think the designers were operating in mils when they created this PCB is because the pitch between these gold fingers here is 2.54 millimeters, or I think that's the equivalent of, is that like 100 mils or something like that? We can actually measure that real quick. Yeah, it's going to be roughly 100 mils. That is the distance between the center of each pin. And the reason I know that is if you look inside your droid, if you look at the connector that these chips, the personality chips, plug into, it says on the side that it uses a 2.54 millimeter pitch for its pins, or its connectors. So I'm going to operate in mils here. I'm going to first take the, well, first off, the width I know is 100 mil. The width here. And I should say, you could do this in millimeters. In fact, the first personality chips I designed, I took my measurements in millimeters instead of mils. It still works out just fine. You're just looking for a rough sense of what the size is here. So I can see it's about 800 mils. I'm gonna go for round numbers here. There'll be tolerance issues. They won't be exactly 800 mils because the tool that cuts the PCB out might shave just a little extra off. But we have a width of 800 mil. We have a height of, I'm going to call that 775 mil maybe, or 770. We can call that 770, 775, something around that. Now the fingers. Now if we notice, there's multiple different heights here. So I'm going to start with trying to get the largest one here, which is that ground pin. It looks to be around 300 mils. So the longest one is about 300. And again, I'm sort of rounding it to the nearest large number, just because chances are when they were designing these, they were going for those kinds of numbers and not something so specific as, say, 287.5 mils. And if I do this in millimeters, and I'll show you in a second, it doesn't make much difference. We'll call that 270. So I want to get a sense of the spacing here between the different, or the different heights here of these gold fingers. That's about 230, maybe a little bit more, maybe closer to 240. And I'm going to focus, or I'm probably going to look at 240 instead of 230 here. Why? I'm looking for a pattern here. 300 minus 30, 270 minus 30 gives me 240. I'm trying to find what the common sense, or the formula that was being used when the lengths of these fingers were being created. Another thing worth looking at is the distance between the edge of the PCB and the gold fingers. I'm I don't even have that on here. What do I want to write that? Call this distance from edge. And for the middle pin here, it looks like it's probably roughly, I don't know, 70 mils maybe? 70 maybe? And these are just sort of, I'm getting rough numbers here. They don't have to be exact. There's quite a lot of leeway or tolerance here when making personality chips. In fact, I know mine are nowhere near these values. 36, maybe 35, maybe 35, right? So double it, you get 70, right? So that's, again, I'm looking for what the common, what the formula is. The width of the PC of the fingers here, I want to figure that out, and I'm gonna say it's probably about 70 mils maybe, which would mean that the gap between the fingers is about 30. The gap looks more like 40 to me. Yeah, I think it's closer 40-60. So the width is going to be 60 mils, and the gap is going to be 40. All right, so now we've got some dimensions here. We can start looking at designing the PCB. Okay, so armed with the dimensions of the PCB, we can start working on creating it. So if I come over here to the design menu, it says convert to PCB. If I click on that, it's going to ask me, or it's going to warn me here that there are some unfinished nets. What that's talking about is I have pins 1, 2, and 5 here. They're not connected to anything. They don't belong to a net. Nets are all the wires in a circuit that are connected together. They form one net. So for example, this wire here between pin 3 and this resistor, that's a net. This pin here, pin 4 is connected to ground. That's part of the ground net. Pin 7 and 8 here, they're connected to VCC. That's part of the VCC net. And then this connection here between 6 and the capacitor, that's another net. These are all different nets, but pins 5, 1 and 2 aren't connected to any sort of net. So it's warning us about that. It's saying, hey, this stuff isn't connected to anything. Are you sure that's what you want? For now, I'm going to tell it to ignore that problem. I can have it check the nets and it'll just tell me that this stuff isn't connected, or I can just say, no, don't worry about it. Let's get into the meat and potatoes here. And I'm going to start a new PCB design, and it wants me to define the unit of measurement that I want to use, millimeters versus mils. I'm going to go with mils here. It talks about how many layers of copper are we going to have here. It'll almost always be 2, unless you're getting into some very interesting and complicated boards. But most PCB manufacturers support 2 copper layers, one on the top and one on the bottom. That's what we're going to go with here. Board outline. For now, I'm just going to leave it as rectangular. This is sort of a starting place, but we're going to change that later on. We also have a width and height here for that outline. I'm going to leave it as is for now, and I'm going to change it a little bit later. So here we are. We have the memory chip, capacitors, a resistor, and tucked way down here is the board outline. Why it's down here while all of this is up there, who knows? But let me bring this up if I can. Or I'll just select it all. Cut it and then paste it up at the top here. So now we can start designing things. The UI, when we're working on the PCB design is the same, except instead of wiring tools, we now have PCB tools. And we also have a new box here that talks about layers and objects. These represent the different layers of the PCB: the top metal layer, the bottom metal layer, the top silk layer, which is the numbering and the outlines of the components that's printed over the solder mask, the bottom silk layer, top and bottom paste masks. You don't have to worry about that stuff. That is if you would ever order a stencil so that you could place the stencil over the PCB and then spread solder paste over it so it leaves a thin layer of paste over all the exposed pads. That's what that would be for, but we're not going to be worrying about that stuff. Top and bottom solder mask layers, that's if you look at the stock personality chips, that green stuff that I was talking about in the last video, that's the solder mask. Rat lines, that shows you how the components are connected. You can see these thin blue lines here connecting the different pins of the different components here. Those are the rat lines. They show you pins that aren't connected and where they should be connected to. So those are very useful. We definitely want to keep those visible. Board outline is, of course, the outline of the PCB. Multi-layer refers to things that exist across multiple layers. Typically, we're talking about holes that go through the board or vias that connect the top and bottom layers of the PCB together. And then document is where you can put text for notes to yourself or to the manufacturer if you need to do that. So to begin with, I am going to actually get rid of this board outline completely, and I'm going to start from scratch. I am going to create a rectangle. No, rectangle? No, we'll just draw this freehand. The grid size here. The grid size is 100 mils, and I know that the width of the board is 800 mils, so I could do 8 of these squares to get the width. So 1, 2, 3, 4, 5, 6, 7, 8. Is that about right? Sure. So there's the width, and then I can bring it down. I know it's 770. I'm actually going to want it to be taller. And for now, I'm just going to pick a spot like there. And I'll bring it down at an angle, because why not? Bring it back up at an angle, because why not? And connect it back to the corner, and there is a rough outline. And the edges don't quite line up, maybe, because the grid isn't, or the lines aren't being snapped to the grid like I want, but that's okay. We can zoom in and get it so everything is lined up perfectly. You can see I have like an extra node here. I'm just gonna delete that. And we're gonna have eventually what looks like a rough outline of a personality chip. Now the height we'll figure out later. I mean, we can just come in here and change that like so. Not going to be a big deal. And now we can start trying to fit components. So for example, I could, I'm going to highlight the top layer here because that's what I'm on now. I can grab that memory chip, hit R to rotate it. And on a stock personality chip, pin 1 is facing down. So I'm going to leave it like that. And then we can bring in the capacitors, C44 and C42 and R33. I'll just, I don't know, I'll stick it, I guess over here like that maybe. If you look at the rat lines here, these thin blue lines, you can see how they're sort of crisscrossing over each other. For this C44, this capacitor, they're crossing over each other here. They're saying that this wants to go to the ground pin, which is going to be way over here somewhere, or in this case, it's going over to the capacitor over here, and then this side of the capacitor wants to go to pin 6 here. If I grab this capacitor and rotate it, now those lines aren't crossing over each other. So now it's going to be much easier to find a path between this pin here and this pin on the flash memory chip. So I'll just rotate it over here. Maybe I do something like this. Maybe I have the VCC side pointing up, so it'll be close to the flash memory chip. I could bring that over here like this. And then for this, maybe I'll do the same thing over here. Like that. And then the capacitors, you can grab just the reference designator and again hit the R button to rotate it and line it up however you want. Now I need to connect the pins, so I'll just select my wire tool, the same tool that you used when you were connecting wires in the schematic. And I'll click on that, ground to ground, and you can see the rat line between here and here has gone now because I've connected it with a wire. And I can see this needs to be connected here. That rat line is gone. The ground needs to come down here. I'm actually not going to connect those quite yet. I'm going to worry about that later. I can see I could connect a VCC between those two pins here and bring this down further to the capacitor. And I can bring this wire up to pin 6. So everything now but ground is connected. And if we really wanted to, I could just connect these like this and bring a wire over here, up to here. And there we go. Everything's connected. All the rat lines are gone. Our personality chip is done. Well, not really. We're missing the gold fingers down at the bottom. Obviously, those need to be created. But we can get a sense already of where we're at. If I save this PCB design, I can come up to View, and there's 2D View, and there's a 3D View. If I click on 3D View, I'm going to see a little 3D version of what this PCB is going to look like. And that's kind of cool. It's a nice way to sort of get a sense of how things are going to look, how they're laid out. Now, I want to caution you at this point that this is far from the final design of this personality chip. This was just a quick and dirty demonstration of hooking everything up with wires here and giving you the opportunity to see what the PCB looks like right now. There are a lot of things here that are going to change, and I need to add the gold fingers here, but I wanted to give you a sense of what this PCB design experience is going to be like. I'm going to end the video at this point. I think it's a good stopping point. It's been a basic introduction to using easy EDA, creating a schematic, creating a PCB based off of that schematic, using measurements taken from existing PCB, the stock personality chip, and creating a rough design of what the final PCB outline will be here based off of those measurements. It's a good start. There's still a ways to go. In the next video, I'm going to add the gold fingers to the PCB design. Those gold fingers are the contact point between the personality chip and the droid. There's also a modification to the schematic that I want to make this personality chip a little more friendly to memory chip programmers. I'm also going to look at a couple of other things to make this PCB design a little more universal with which memory chip you choose to use. For example, the pads for the footprint, I should say, that we're using right now is for a very small, that 150 mil package memory chip. I want to extend the footprint, those pads for the pins. I want to make them wider so that this PCB design could accommodate larger memory chips. We saw a 200 mil, and I think Winbond has a 209 mil footprint for their memory chip. So I'm going to make that footprint a little bit bigger so it could accommodate different sizes of those surface mount memory chips. And then I might also add a DIP 8 footprint so that you could use a through-hole memory chip. How I could fit that into this design, I'm not sure. That's going to take some tweaking, some playing around. I'm not even sure if it's going to be possible with the larger surface mount footprint. We'll see. There's still a lot to be done here, but it's underway. The project is moving forward, and that is what I'm trying to do. So until the next video, have fun.